in linear algebras, we study vector spaces, and the morphisms between vector spaces are the linear maps. Now, when we have when we have now a topology or a metric, then what we are also interested is that these maps that preserve that behaves well with the topology. So now, if you have two vector space V1 and V2, then we will consider linear maps from V1 and V2, and we might need or not to assume that this linear maps is also continuous. So let's make some simple observation in finite dimensions. So if V1 and V2 are finite dimensional vector spaces, then remember that there is only one possibility for the topology of V1 and V2. So whatever norm you choose, and in particular, so what one can prove is that then every linear map, we can think of representing it with a matrix after we choose basis. Every linear map is continuous. However, in infinite dimensions, the same is not true. So in infinite dimensions, it may not be true. And also see that, I mean, it's not even clear what is the topology for V1 and V2. So, and also notice that V1 and V2 don't have a canonical topology, because we haven't specified the norm, and a priori two different norms may give two different topologies, differently than the finite dimensional case. Okay, so which means that now if we want to have some connection with the topology, or with the topology given by the norm, we need to assume that the map are also continuous. So what is interesting is that one can give a characterization of continuity in terms of the norm in the following way. So I'll give first the definition and then the proposition. So suppose we have norm spaces. So if I write here V1, I actually mean the pair V1 and a norm, when this norm is the norm on V1, and likewise V2 as a norm. Okay? So now I choose T from V1 to V2, a linear map, linear transformation. We say that T is bounded if restricted to the unit ball is bounded. It is bounded. So it's bounded image, i.e. there exists C such that if X is in V1 and norm of X is less or equal than 1, then the norm of Tx is less than C. Okay? Remember, notice that a linear map cannot really be bounded unless it's 0, because as soon as Tx is different than 0, then what we have is that T of lambda x is equal lambda Tx, and this goes to infinity as lambda goes to infinity, right? So a linear map can never be bounded as a map. So we use the term bounded to mean that it's bounded on the unit ball. Equivalently, one can say that T is bounded if there exists C such that Tx is always less than C times the norm of X. This is for any X in V1. Okay, so first of all, one should understand that this is a norm in V1 because this vector is in V1, while this vector here is in V2. So this norm here is a norm in V2, okay? So we will, when the point is clear that lives in a space with a fixed norm, we will not make a new symbol for the norm, okay? Now, and this definition is equivalent to this exactly by linearity, right? Because you can always divide any vector V by its norm, and then it's going to be the unit ball. So in the unit ball is going to be bounded by C, and now when you move the norm out, you will get exactly this function, this equation. Okay. Now I will prove that this is equivalent to being continuous. And here's the proposition. So T from V1 to V2 linear, then the following are equivalent. One, T is continuous. Two, T is continuous at 0, point 0. Three, T is bounded in the just defined sense. Four, T is Lipschitz. It's a Lipschitz map with respect to the distance induced by the norm. Okay, proof. Okay, if it is Lipschitz, then it's obviously continuous, general fact. If it's continuous, in particular, is continuous at 0. Oh, all of this is clear. Okay, let's prove that 2 implies 3. Now, if it is continuous at 0, then for any epsilon, I can choose delta, take epsilon equal to 1. There exists delta greater than 0, such that if I look at the image of the delta ball, is contained in the unit ball. Okay, so these are the elements in this is in the image. Wow. Okay, so what does it mean? This means that if the norm of X is less than delta, then the norm of Tx is less than 1. Okay, so now we will take an arbitrary X in V2, say X is different than 0, otherwise there's nothing to prove, but because it's linear, so we can choose delta over norm of X times X. So now this becomes a point in the ball that is delta. And so what we have is that, okay, its image as norm less than 1. And now we use linearity of T plus the fact that the norm, so scalar, positive scalars go out, and we have the required property, right? So i.e. the norm of Tx is less than 1 over delta norm of X, which means T is bounded. Now, if T is bounded, let's prove that it's in fact Lipschitz. So let's take 2 points, x, y, in the first vector space. Then what we have the t of x minus y. So t is bounded, so this norm is less than a constant times x minus y. However, by linearity of t, this is the norm of tx minus ty, which is exactly the distance of tx and ty, while this one was the distance of x and y. So we proved that the map is Lipschitz. We will see next how naturally the space of continuous map from a norm vector space into another one form a norm vector space. So here's the definition of the operator norm. So if you have a linear operator between norm vector spaces, we defined the operator norm of t is, so it's denoted as the norm of t, it's the supremum of all the values norm of tx such that x is in v1 and the norm of x is less or equal than 1. Okay, so first of all, this is a norm in v1, this is a norm in v2, and this is a new symbol that we are defining. Also, this inequality can be equivalently replaced with strictly less than 1 or equal all equivalent because of linearity. The maximum is obtained when the vector has length 1. Okay, and therefore with this definition, just make you notice that t is bounded if and only if its operator norm is finite. And which we prove is the same of t being continuous. Okay. Now we define the space of linear maps between v1 and v2 to be the linear maps, linear and continuous. Okay, so in this symbol there is no continuity written, but we only reduce to the continuous linear maps. Okay, so this space is going to be, this is a vector space, and this is a norm on this vector space. Let's write it as a proposition. Proposition. If v1 and v2 are norm vector spaces, then lim v1 v2 equipped with the operator norm is a norm vector space. Notice that the operator norm depends on the norm chosen on v1 and v2. Oh. Proof. Okay. So first one should realize that this is the linear maps form a vector space. Okay, but now let's check that also. Okay, the sum of two continuous functions is continuous, but we will see it again. Okay, so I'll make you notice that if T1 and T2 are linear maps from V1 to V2, are linear, then okay, the norm of the vector Tx, T1x minus T2x, right? By triangle inequality, this is T1x plus T2x. And so what we understand is that if on the unit ball these numbers are bounded, then this number is bounded. So if T1 and T2 are bounded, then T1 plus T2 is bounded. And moreover, the norm of T1 plus T2 is less or equal than T1 plus norm of T2. Okay. And now one should check that all the axioms for vector space and norms are also satisfied, but they're all very simple. I will just write that all other axioms of vector space and norms, right, are trivial. Except maybe one thing that I want to comment is that if T has operator norm 0, then this means that Tx is equal to 0 for all x in V1, which is the same as saying that T is the constant equal to 0 map, linear map. Okay. Like for a space, we have a set of very big importance is the class of functions from the space into R. Then in case of a norm vector space, it's going to be important to consider the continuous linear maps from the vector space into R. And to this we'll also give a proper name. So suppose we have a normed vector space, and we will denote by V star the space of linear maps, continuous linear maps from V to R. So this is the space of continuous linear transformations and it is called dual, the dual of V. Okay. Let's a few facts about the fact that we are restricting to continuous linear maps. So if V is not complete, then there exists explicit non-continuous linear transformations, linear maps, linear forms. I say forms, transformations, or maps, you see. But so if V is a Banach space, so it's complete, then it's actually much more difficult to construct non-continuous linear forms. But one needs the axiom of choice to prove to construct non-continuous linear forms. Okay, but so let's start the dual. What is very interesting of the dual is that no matter what is V, the dual is always completed. The reason is that the linear space from V1 to V2 is a complete metric space as soon as V2 is complete. Since R is complete, this will be the case for the dual. So I will just prove it for the dual, but it's a more general statement. So if you have a normed vector space, so not necessarily Banach, then V star is a Banach space. So this will make our life easy. So as soon as we can construct a norm vector space as a dual, then we'll get it for free that is a Banach space. So proof. So let's take a sequence T star that is Cauchy. So yeah, it's Cauchy. We have to show that it converges. So let's remind what it means. It means that for any epsilon, there exists some n, such that for all n and m greater than n, the norm of Tn minus Tm is smaller than epsilon, right? This is what it means to be Cauchy in the dual space. Okay, so what it means that the operator norm is less than epsilon. So it means that for any x, Tnx minus Tmx in norm is less or equal than epsilon norm of x for all x in V. Okay, so now let's fix some x. And now look at Tnx as a sequence. So first of all, Tnx is a real number, right? So Tx are valued into R, and moreover, because of now the norm of x is fixed. So this property here will tell us that these numbers form a Cauchy sequence. So Tnx is a Cauchy sequence in R. And actually, you will see that this is the only property that we need of the target. So we need that R is complete. So Tnx converges to a number in R, which we denote by Tx. Okay, so in other words, what I'm saying, I'm saying that Tn converge to T pointwise. So we prove that these functions converge pointwise to a function. Okay, now since each of them is linear, write the condition to be linear, pass to the limit, and what you get that T is also linear. Okay, now let's check first that this is actually a bounded linear map. It's continuous. There is no reason why the pointwise limit of continuous maps is continuous. And then we will need really to prove that we have convergence of Tn to T in the space of V star. So new page. Okay. We check that T is bounded. So we take X in V1, in V, with norm of X less than 1. Okay. So we have that for the previous epsilon and n, for n and m greater than capital N, the norm of Tnx minus Tmx, we proved this was at less than epsilon norm of x, but now the norm of x is 1. Now what do? We take, in this equation, we take the limit. So we fix n, but we take the limit of m going to infinity, and what we get is that the norm of Tnx minus Tx is bounded by epsilon. Okay, so what we get that the norm of Tx by triangle inequality is the norm of Tnx plus norm of Tnx minus Tx. Now, the first one is less than the norm, operator norm of Tn, and this one is less than the operator norm of Tx, because x is in the unit ball, and this is less than epsilon, plus epsilon. This is finite number, right? So, which is finite since Tn is bounded. So we don't have to take the limit in n. Okay, fixed n, Tn has a bounded operator. Okay. Okay, so we proved that the operator norm of T is finite, so T is bounded. Okay, so T is finite implies T is in V star. Okay, now the last thing to check is that need to check that Tn converge to T in the norm of V star. Okay, but now looking at this property here, what we have proved exactly that what we proved, that if n is greater than n, then the operator norm of Tn minus T is less than epsilon. So let's call this equation 2. So what we get is from 2, we get that if n is larger than capital N, then operator norm of Tn minus T is less than epsilon. So the operator norm of T minus T goes to 0. This is the end of the proof of the fact that the dual of any vector space is a Banach space.